Now, as we go into Cartesian product of sets, this is a special way to link up ordered pairs, and it's written A crossed with B. So set A crossed with set B. This was developed by a French mathematician, René Descartes, and referred to as Cartesian product of sets. And the law or rule for it is that set A crossed with set B such that AB, now notice this is an ordered pair. A is an element of set A, and B is an element of set B. So let's take a look at this. So I wrote this out just a little different way, but basically they're asking us to find Cartesian products, that is, with set A and B, A crossed with B, and then reversing B crossed with A. And in the video produced by the authors, I like the way they show and arrange it. That here we have 3 values in A, so we're going to get 3 rows where we just pick up the letters or the numbers 6 and 7. So the 1s, the 5s, the 9s, and then we add the 6 and 7, 6 and 7, 6 and 7. So we get this form of display where, since there are 2 values of B, we're going to get 2 columns this way. Now, in the other cross, when we reverse it, notice our 6 now is our first element, and then we pair it with each of these letters. So since there are 3 in the second group, we get 3 columns, now 2 rows. So pretty straightforward. These are Cartesian products, and this is the display of them. And they are asking us to note that in the sets, order was not critical, but in the ordered pairs, order is critical. And we see that mentioned here, where they're saying that A crossed with B does not equal B crossed with A, because order was important. Now, this rule deals with the cardinal number. You remember the sub n is the number of elements that you would have. That, generally speaking, up over here, you recall we had a certain number one way, and even though the order was different, we had the same number of elements the other way. So this is just saying that that is true. And the basic rule will follow that if in set A there is 1, 2, 3, 4, 5, 6, 7 elements, here there are 3. So 7 times 3 will be 21. And here in set A they're saying there are 24. And in set B the cardinality of it is 5. 5 times 24 is 120. So something easy. We're now going to take a look at operation. Is a rule or procedure by which one or more objects are used to obtain another object. The most common operations on sets are summarized in the following box. So let's take a look at it. Now, this is a summation of what we've been through so far, and we can see it represented in the Venn diagram, that when we speak of a complement of A, which is written A prime, and is defined as this, it would be all elements not in A that are in the universe. So there's set A, and there's the complement of A. When we look at intersection, we're looking for those parts of set A that are also found in set B. And there is the Venn diagram. And the symbol for intersection, remember, was this upside down U. Now, union is where we combine all elements of A and B. The difference, we said, where we have, let's say, set A, and we're subtracting set B, in a Venn diagram would look like this. And we just finished defining the Cartesian product. There is no Venn diagram for this. Now, as we look at more on Venn diagrams, we have three figures, and here there is one set, two sets, three sets, and the numbers that are used within these sets are not elements nor cardinal numbers, just to relate to parts of the diagram. So it's just keying these numbers to parts of the diagram. For instance, in figure 11, 3 includes the elements, or is included in both set A and set B, while 4 indicates it's not in set A at all. And if you see this 4 in this diagram, you see is included in all three sets. But then they say, what does region 7 say about all of this? How would you describe that? Well, 7 is in B and C, but not in A. So the numbers are just to be able to state things about the Venn diagrams as we see it illustrated here. Now, in example 9, I would suggest, and of course the text suggests this as well, that you pause, we'll pause, look at the Venn diagrams, the figures that are illustrated, and then try to get the meaning of what they're asking and what they're showing here. So let's do that. Now, as we build a Venn diagram to represent sets, that's going to be a very useful tool in figuring out things. In letter A, we're asked to look at the complement of A in union, in intersection, I should say, with B. So what would the complement of A be? A prime. Well, it would be everything outside of A. So I shaded it in. This is the complement of A. Now we're looking for an intersection with B. So I have now added B as green, but we want just the intersection. That is where the blue and the green are found together. Well, for that we would have to take out this little portion right in there, as we see in this illustration. So we see in the summary of this, a complement, which was all of the blue area, including this little part here, but intersecting with B, which would have been all this green of B, but the part where the blue and the green are is what we see that's left. So this is our first one. Now let's take a look at the second. So in letter B, we're asked for a union of what the complement of A would be, and that would be what we had originally, everything except what is in A. And then for B, everything that's except in B. So the part that wouldn't be covered then in the complement of both is where A and B intersect. And you could pause it again and read this description in more detail. In example 10, they're asking you to locate elements in a Venn diagram. So they're giving you the universal set, and then they're placing some of these members in set A and some in set B. Now you know there's an overlap because our T is found in both A and B, and the V is found in both A and B. So there's our TV. And the only other element out in letter B would be the X. And looking at this carefully, you see how they put it together. So again, patience, careful placement and study to figure out what this would look like. Now, those that are not in A and B are placed in the universe part of your Venn diagram. Okay. And I had paused the tape, of course, to study this, and this is what we'll do. But complement of A is everything outside of A. Complement of B, everything which is outside of B. And notice that C keeps getting colored in. So as we find the intersection of that, the only intersection of these two complements is C, this part here. And we are now saying that C is what is in common with this as we look for the intersection. So this is what we have. And again, they give you much more detail as you look at your textbook and study this. And this may be a good time to review. I know I could always use review. The symbol for element or a member, symbol for subset, and proper subset is without the line. Remember, that is one less than exactly the subset. For example 12, when we're using a Venn diagram to verify a statement. Here they're saying statement A or set A and B are subsets of U. We know that generally that is true. Is the statement that the intersection of sets A and B, their complement, is equal to the union of the complement of A and the complement of B? Is that true for every choice of sets A and B? Well, to find the solution, you'd have to use your textbook and then page back to look at these diagrams. We'll see some of this on the next page. And as you see here, when this is shaded, this is shaded. So this is a true statement. Let's go on now to De Morgan's law, which we have just proven that the complement of the intersection of two sets is equal to the union of the complements of the two sets. So interchanging the word intersection and union produces another true statement. The complement of the union of two sets is equal to the intersection of the complements of the two sets. And these laws were published by the British logician Augustus De Morgan, and he was profiled on page 22, and they're stated as De Morgan's law, which we see right there. Now, I'm not expecting you to memorize this, and that's why your notes are going to be very important if you need to reference this. And having your notes and being able to understand what's written there is also an important skill. Now in figure 17, strongly suggests the truth of the first of De Morgan's law. They provide what is called a conjecture. Conjecture is actual proof of De Morgan's law, would require methods used in a more advanced course in set theory. Well, we've gotten pretty far so far, and although I'm sure that it gets more complicated. All right, example 13, describing Venn's diagram regions using symbols. And for this, we're allowed, or they want us to use set A, set B, set C, the symbol for intersection, the symbol for union, and the symbol for difference, and the symbol for prime. Or complement as necessary. So again, we'll pause here, let you take a look at it, and see if what they've written makes sense. Note there's more than one way to write it. Here they're saying the intersection of set A and B with the intersection of C. So the intersection of A and B with the intersection of C. And here is sort of the associative principle where you're doing A with this intersection, or without parentheses and just the intersection of these three sets. So that one wasn't too bad. So in looking at example B, we notice that B is shaded. So they're saying that B is intersecting with the complement of A. So there is the complement of A, everything that's not included in A, and it's the intersection of then the complement of C, everything that's not in C. So the part that would be intersected is this. Or we could combine set A and C together and subtract it, that would be the union, but subtract it from B. Or another way, as they're illustrating here, B intersecting with the complement of A and C, which is similar to what we had there. And you need to study and again look at it, study, look at it, study, and contemplate. It is a challenge. Not sure how much class time we may have left, but at the exit of section 2.3 there are these exercises. Section 1 and 2, they're asked to match. So we may have some assignments depending on class time, and we'll pause.